Spring break, this is the real-time digital signal processing lab class at the University of Texas at Austin for the spring 2014 semester. So this was a test right before spring break, and we'll go over solutions for 1 through 3, and then we'll talk about solutions for problem 4. That's a good kind of place for short discussion. So we'll go right on into, so 4 problems on the test, and I suppose they got, I intended them to be more difficult 1 through 3 and a little bit easier on 4 versus 3, but your experience is going to be yours and not necessarily what I envisioned, but that's what I had in mind. Problem 1, so this is all about biquads. Did a lot of biquads in lecture and in lab, and also we've done IR filters in lecture and homework. And so anyway, so this is right out of lecture 6 slides, and part of this is also out of homework sets 2 and 3. And I guess you go back to 0 for the block diagram, so it's all the above on homeworks. All right, so here it is. So I went ahead and expanded the polynomial up here. So this is a biquad in pole 0 gain form. So we have a list of zeros, Z0, Z1, a list of poles, P0, P1, and a gain, capital C. And at this point in the problem for part A, we're not ready to, in fact, we don't really see to anything in this problem. In the end, you can set it to 1 if you like. It doesn't change. In part E if you want. Right now I'm just asking you to work with the factored form and then give it the unfactored form and then find the coefficients as a result. So here are the feed-forward coefficients. And as we make mistakes, we'll correct, solution set as we find mistakes. Here's B0, B1, B2. A0 and A2 are a little bit unusual. They're the negatives of these. Right. And the reason for that is that, when we convert this back to a difference equation, we multiply both sides by the denominator and then do the inverse transform. So and then we move over these terms from left to right, so these will be negated. All right, so that's it. Oh, I should probably pause and say these are pretty good problems to be aware of for interviews on campus, on site. These are really good questions for these kinds of things. Problem 3 more for an on-site, not on campus question. It's a little more involved. But it's pretty good question about biquads, and one of the reasons that we care about this expansion to unfactored form is this is where we start seeing perturbations or distortions in the pole locations. If we add 2 32-bit floating point numbers, we're going to lose a bit here. If we multiply 2 32-bit floating point numbers and put it back into 32-bit float, we're going to lose 24 bits of mantissa plus sign. We get a distortion in the pole location, which can lead to instability when implemented. We tend to expand this only for biquads just to control the amount of distortion in the actual pole locations due to this expansion. Again, the filter design algorithms return pole zeros and gain, and this unfactored form is good for implementation as a biquad or in biquads. Difference equation. You can do this from either what we talked about in lecture 6 slides, or you go through the long process of doing the inverse Z transform by noting that the Z transform, the transfer function, is just the ratio of the output Z transform to the input Z transform, and then work backwards to the difference equation. But this is what we've implemented. We've talked about this quite a bit in lecture, and you would have implemented this possibly in lab, but didn't need to have done that for the test. This is right off of lecture, in lecture 6 slides. Initial conditions, talk about that both in homework. Do that homework problems, I guess homework sets 1, 2, and 3. So initial conditions are just the initial x of minus 1, x of minus 2, y of minus 1, y minus 2. And they have to be 0 for LTI and causality properties. But you can always see this if you need to derive it, which we've done homework solutions, is by just getting the initial, look at the initial output value, and you might go ahead and compute y of 0 and then also do y of 1 just to make sure. And you'll see the initial conditions come right out of what happens at the first output value. That's another way to get it. You can also, if you do the block diagram form that's direct form, you'll see the initial conditions because every initial condition corresponds to one delay block. There are lots of ways you can get the initial conditions. Block diagram, I did the one delay line form down the middle instead of the two delay line. Either one's fine. You have delay line along the inputs, delay line along the outputs. We just have to have feedback here for an IR filter. It happens. Also, I guess I should comment on tests. You know, it's hard for me to know if you made a mistake because you're in a hurry, you're under stress. It's a time test. It's 50 minutes. So I don't know. So this is where it's good for you to look at what you did on your test to see what it was. I don't know which it is, whether it was just a, pressure or stress and you just made a silly mistake, or it's something that you want to reinforce. And you'll know that. I won't know that. Okay, on to part E. Now, see, nowhere along the way have we set C to any value. This was not a you really can't set the constant C to a value that's tuned to a particular frequency until you know the selectivity of the filter. So there's, I mean, if you students did that, it just cost a couple of points. It just wasn't needed here. Now in part E, we now know the selectivity, so we could, if you wanted to in this problem, I didn't ask in part E, you could have set C to something. You could have set C so that the response at zero frequency is 1, for example, but it wasn't necessary for this problem. So two zeros and 2 poles, and I went ahead and added a trivial pole in there. I suppose I could have put the pole at 0.1 to see what you would do. It doesn't change much. A pole at 0.1 doesn't really affect magnitude response much. A pole in the origin doesn't affect magnitude response at all. It affects phase. It's a linear phase term. But it does not affect magnitude response at all. Anyway, so two zeros and 2 poles. There's a double zero at -1. And I think a few people interpreted this as -1 and 1. I think it's probably that was probably just speed, stress. That does change the answer quite a bit. If it's -1 and 1, I get a notch and a low pass filter combined. It's weird. It's kind of a weird combination. All right, but the intent here was a low pass filter. Right, the pole tells us the pass band centered at 0, since the angle here of the pole is 0 with respect to the positive real axis. And then the zeros tell us there's a stop band centered at pi or minus pi. It's a low pass filter. Any questions on problem 1? Did a very good job on problem 1. Even if you didn't get full points, there was people just did a great job on this one. A couple people had trouble here and there. One person gave me a feed-forward system instead of feedback. Again, I don't know. That's stress. I do all the grading for the tests. No one else grades. But again, a good job on this one. Really good job. A few things here or there, but minor, typically. Any questions on problem 1? Okay. Problem 2 got a little bit harder, at least for part A. Part B is a lot like previous tests. All right, so for problem 2, this question involved the following. So I tell you, so in smart grids, communication between customer power meters and a local utility can occur over the outdoor power line. Give you the transmission band from 40 to 90 kilohertz. Sampling rates at 400 kilohertz. This is a real system. And I asked you to consider the following sources of distortion, so additive noise and a narrowband interference. This is right out of question 3.1 in homework. So consider, and we talked about these things too in lecture. So I'm going to give you a cascade of 2 filters. The first filter is going to be the bandpass filter to attenuate out-of-band additive noise. And then we'll try to cancel the narrowband interferer with a notch filter. So the part A was tough. A lot of difficulty on part A from what I saw. So I asked you to design a 6th-order FIR filter to reduce the out-of-band additive noise by manually placing zeros on the pole zero diagram below. Now, even with that, I got a lot of answers with poles in them that were not at the origin. Of course, you could argue there are 6 trivial poles at the origin. That's fine. I don't show them here. I do make a comment about them. So again, I don't know if that's, again, the pressure of the test or what. So first I have to find out where the passband is. And we know we want to pass frequencies from 40 kilohertz to 90 kilohertz, and the sampling rate's 400 kilohertz. So the range of frequencies we care about are from pi over 5 radians per sample to almost pi over 2, so 9/20 pi. There are many solutions for this. The one I propose here is we want to put a zero. We want to put zeros in the stop bands. We don't want to put zeros in the pass bands. It's not a pass band anymore. So this first filter is just a bandpass filter. So I can put 1 0 here and my other zeros here. I want to keep the zeros away from the pass band. Right, we want to allow some transition between pass band and stop band. And they should be conjugate symmetric or real valued zeros. Okay, again, I think some people drew zeros in there that were not conjugate symmetric. They might have just, again, speed, pressure of the test. Go ahead. Yeah, it's not, on the previous question on 1.1 part E, I specifically pointed out a pole at the origin. On this one, there are 6 trivial poles at 0, and you can certainly put them in there, which we can do. Here, I just omit it here in the. Go ahead.
We have trivial poles.
Well, if you have any non-trivial poles, then you have an IR filter immediately. So if you have any poles that are not at the origin, you immediately have an IR filter. Again, not that FIR is good and IR is bad. No, but it's just that here I'm asking just for an FIR filter. That's all. And then the second part B, I'm asking you to go ahead and design the IR filter to remove the 50 kilohertz interferer. All right, so here's part A anyway. So any questions on part A? Okay. All right, so another solution you could have come up with, you could have put 2 zeros here, or a round on either side of the z equals 1 point, omega equals 0. And you could have put 4 zeros over here. That would have been a pretty good one, too. You just want to make sure you keep the zeros away from the passband, right? Because ultimately our IR filter is going to have some poles indicating, well, the filter to come is going to give us a pole here. We want to kind of stay away from the poles that could be in the passband. All right, so this was tough. So a lot of people had trouble with this one. Any questions on this one? My initial version of the question was a 9th order filter, and it's way too many zeros to draw. So I probably should have done maybe 5 or 4 would have been enough. But okay, so part B did very well. Wow, part B. So many people got it. Oh, there's someone that got a perfect score on problem 1, raw score, no curve or addition, and there are number 1 or 2 that I think 2 got perfect scores on this one, and 3 got a perfect score on number 1. Okay, so this was a lot like previous tests, right? So again, I have an FIR filter. It's going to be our bandpass filter to attenuate out of band noise. The IR filter is going to be a notch filter to remove this 50 kilohertz interferer. This is a real interference source. It turns out in power line communications, we get a lot of interferers in the 20 kilohertz to 100 kilohertz bands. They have to do with amplification in the ballast of transformers. Basically, any DC to DC converter, buck converters give you these kind of harmonics. They're in many different power systems in a house. This is a really common problem, having this kind of interferer. Anyway, so this particular interferer is at 50 kilohertz, so where does it reside in discrete time? With a sampling rate of 400, we know how to do that. It's 2 pi f naught over fs. This gives us ultimately pi over 4 radians per sample, 45-degree point. You don't have to draw the pole zero diagram. I just do it here for illustration, I suppose. So the zero locations should be on the unit circle at the angle omega naught, and then the pole should be slightly off the unit circle, slightly inside the unit circle at the same angle. We have our notch filter at omega naught. You did great on this one. I've asked lots of notch filter questions in the past. It's one of my favorite questions. I will tell you these are really hard to get right in fixed point arithmetic. Not that you have to worry about that in lab because it's floating point, but you need a lot of extra precision to get this right in fixed. They're painful to implement. Yes?
Around
Yeah.
a little bit, and since they won't be aligned on each other.
That's exactly right. You really need them to be aligned on the right and the same angle, and you start messing with their locations. That's right, you get perturbations. But also the intermediate calculations need to be held to higher precision as well. Okay, so these are often done in fixed point at 24 bits, not at 16. It's hard to get right. Okay, next up is part C. Now again, I think there was, this one, folks missed a little bit on part C, I think mainly because of speed. Maybe just going through the test pretty fast. I gave, in the question I asked you, how many instruction cycles on the particular, TI, digital signal processor we're using in lab, will it take to compute one output sample Y of n given one input sample X of n? Now, I was referring to the block diagram, and I think, again, you're going through this fast. I guess I could have been more explicit, but I intended for this X and this Y, and probably about a third of you gave me answers for one of the filters, but not both. Again, I think it's just from going through fast. This was in homework 3, question 3. Spent a lot of time on this particular issue for both biquads and for FIR filters. So there's a handout that I did record as part of lecture 6, part 4, when I recorded that lecture, and that's referring to Appendix N in the course reader. So this thing, it's assembly code that's sort of pseudocode, but it's n plus 28, where n is the number of coefficients in your filter. This works for either FIR or IR, either one. And so as long as you can figure out, so for a 6th order, I think where people had some trouble is for a 6th order FIR filter, how many coefficients? 7. That's caught a lot of people. So you didn't lose too many points there. And then for the biquad, there are 5 coefficients, right? There's the 3 feed forward, B0, B1, B2, and the 2 feed back, A1, A2. So there are 5 coefficients. And again, the number wasn't, if you did all this right and used a different offset, you used 26 instead of 28, you would have gotten full credit. It's not about, is it exactly 68? It's how you went about finding the answer. So people would have lost points here that 7 wasn't the right, they used 6, or 5 wasn't done here. It was some other number for the IR case. All right, again here, problem, part A was the difficult one. All right, problem 3. This was a really tough question. I will tell you, this is this is a tough question. So part of this is, all right, so why did I ask it? This gives you a very quick way to design a analysis filter bank from one filter. That one filter, in this case, is a low-pass averaging filter, but it could be any low-pass filter. It could be an FIR designed from Parks-McClellan. It could be a Hamming window. You start with one simple low-pass filter, and we can build up a way to do essentially spectrum analyzer. This is now going to divide this input signal X of n into uniformly spaced frequency bands, each spaced 2 pi over n in width. Go ahead.
Changes the band a little bit.
Well, each time you convolve X with H, you're going to be filtering, right? So I'm running X through this. The same input goes through all these filters in parallel, and the output here will depend, of course, on your low-pass filter design. The way I've set it up is this low-pass filter should have a bandwidth of 2 pi over n, right? The whole frequency band in discrete time goes from minus pi to pi, which is 2 pi in width. So if we divide that into n subbands, we should get 2 pi over n as the bandwidth. So again, any low-pass filter is your starting point. You can do this for audio analysis, speech. You can do it. We can make a 2D version of this and do it for image. Lots of applications here. And it's very simple. Once you have the first filter, the rest come right off that one filter. The fancy name for this, I didn't write this down in the homework set. Let me annotate this. So this is my low-pass channel. And then I'll read the question just a second. All right, so I have a number of channels. And we talked about decomposing things into 2 channels when I did Lecture 5, Part 1. We talked about a 2-tap averaging filter and a 2-tap difference to divide the input signal into low-pass and high-pass channels. This is a generalization of that discussion into n different filters, as we had in the lecture. All right, so the fancy name for this is called a cosine modulated filter bank, and you'll see the modulation show up. So this is a cosine modulated filter bank. It's a pretty advanced topic. It's my problem 3. I like tougher problem 3s. There was one student that got a perfect score on this. It's doable, and so it's possible. Very tough question. All right, so let's go ahead and read it through. So it's a filter bank design. Shown on the right is a bank of n filters to decompose a signal x of n into n frequency bands. Now, I don't tell you here they're equally spaced, but they will be equally spaced. Each filter has a finite impulse response. H naught of n is my low-pass filter. The last H sub Kaplan minus 1 of little n is the high-pass filter, and then all the other filters are bandpass. And each filter has n coefficients. So when n is 2, this reduces to 2-tap averaging, 2-tap difference. Or first-order difference and 2-tap averaging. Normalized, if you want to. If you want to, you don't have to normalize, but. So 2 channels, 2 coefficients. So if I have 3 channels, each filter will have 3 coefficients, and so forth. All right, so first up, I tell you let H naught of n be an averaging filter. And what's the null bandwidth? You get the null bandwidth a couple different ways on this one. Actually, probably even you're very creative on this answer, by the way. Some very interesting answers on this one, and they were correct. So the way I'll look at it, and I'll tell you the way I heard some of you go about this question. What's the null bandwidth? Well, first of all, here's the averaging filter impulse response. It's a rectangular pulse. And going back to homework 0, my favorite homework set, you looked at rectangular pulses. And the null bandwidth for a rectangular pulse in the continuous time case is 1 over the length of the rectangular pulse. Right? It is, because the Fourier transform of the rectangular pulse is a sinc, that first 0 crossing is at 1 over the rectangular pulse length in hertz. And in radians per second, it's 2 pi over the rectangular pulse length. So you could infer that, the frequency here would be, the null bandwidth would be 1 over n, or if I want to do in radians per sample, 2 pi over n. And I think only a couple of people took this route. This is not the usual route. One person said, gee, that the answer was in the homework solution set, and the student was exactly correct. So I explicitly make this comment in the solution set for problem 2.1. All right, now what other people did is looked at this and looked at the transfer function in the z-plane. All right, it's a polynomial in terms of z to the minus 1, and noticed that all the zeros are uniformly spaced around the unit circle except z equals 1 is missing. And the phase, let me draw this. It's getting a little bit too difficult. So when I create the final solution set, I'll have the alternate version. All right, so students noted that for this particular averaging filter, or for an averaging filter in general, I have these uniformly spaced zeros around the unit circle, but I'm missing 0 at z equals 0. Z equals 1, I'm sorry, angle of 0. And noted that this angle was 4 pi over n, and that means the bandwidth was 2 pi over n. Now, I didn't cover this, so I don't, this came from somewhere else. But it's correct. It's correct insight. So the null bandwidth, which is where the first 0 hits, is 2 pi over n. That's a good answer. One I hadn't thought of. All right, so that was, so you get, so what, how does it do part A? I think that was it. Tough question. Group delay in all 3 cases has to do with impulse response symmetry. And so if you remember, not all FIR filters have linear phase. But for an FIR filter, the group delay is constant if the impulse response is either even symmetric, which is linear phase case, or odd symmetric, the generalized linear phase case, if the symmetry is about the midpoint of n minus 1 over 2 for n coefficients. So that's the midpoint of the FIR filter's impulse response. And we've derived this a couple of times for the 2-tap averaging filter and the first order difference. And we always pulled out the phase shift equal to the midpoint in time. And from there, we found that we got a linear phase times an amplitude function. We did this in lecture 5, slides 17 and 18. All right, so, and we've talked about this quite a bit. So you don't always have linear phase for an FIR filter. I saw several claims for that in your answers. An FIR filter doesn't always have linear phase. We'll see many cases in the second half where it's not true. It's true that the FIR filters we've seen so far in class have had the symmetry, either even symmetry about the midpoint or odd symmetry about the midpoint, but that's not always the case. But when it is the case, we have constant group delay. And so in this case, for the averaging filter, which again, we did the 2-tap case in lecture, this has even symmetry about the midpoint in the impulse response. And that means that our group delay is going to be constant n minus 1 over 2. All right, now it's going to get tougher, much tougher. So in part B, I'm asking you to derive the high-pass filter. And this is a really hard problem. So I said derive the filter, this high-pass filter from the low-pass prototype H naught of n, and I tell you how to do it. So I give you this G of n, which alternates from 1 minus 1, 1 minus 1. And it could be two-sided. Here I draw the product of H naught and Gn. So the product is going to alternate 1 minus 1, 1 minus 1, and it's going to be finite in length, based on the length of H naught of n. And G of n, the key is to notice that G of n is minus 1 to the n, which we've talked a lot of in class, and this is the highest frequency possible in discrete time. And this is e to the j pi n, which many of you correctly noted. You can also write this as cosine of pi n. So it's going to alternate 1 minus 1, 1 minus 1. It's the highest frequency possible in discrete time. So the product in time means that it's a modulation. So it's a modulation problem in disguise. It's cosine modulation. So I'm just multiplying cosine pi n times H naught of n. And whenever I multiply, and we didn't do this explicitly in the time domain, it is true, but from the intuition from the continuous time case back to homework 0, if I multiply by cosine in the time domain, I'm going to shift the Fourier domain by the frequency of the cosine left and right. Right? So I start with a low pass. So I start with a low pass, my low pass averaging filter, and after I multiply by this 1 minus 1, I shift by pi to the right and minus pi to the left, and I get this. All right, so there's another trick here. So if I want to change a low pass to a high pass filter, I can just multiply by minus 1 to the n, the coefficients, or the impulse response. All right, again, we have symmetry in the impulse response. Here I show you the impulse response. So I have odd symmetry about the midpoint. So this has linear phase, generalized linear phase, and the group delay is n minus 1 over 2. Part C, try to make this a little more tractable by asking you to do the three coefficient case. So you could get your hands on all the values more easily. So here I'd say now let's try to get the bandpass filter, H1 of n, from the low-pass prototype by multiplying the low-pass impulse response by some sinusoid. And I ask you that we want to send to the bandpass filter pi over 2. Now there's some creative answers to this one, and they were pretty good. I had to go back and think about it. So some folks correctly, this is infinite impulse response. If you think about it, it's not a filter, it's five-o unstable. But it's an LTI system that's two-sided, a two-sided signal. And so about half a dozen of you said, okay, well, if we need a bandpass, if I want a bandpass filter, I'll just go ahead and design an IR filter with the poles in the right location. I'll use that impulse response for G1 of n, which works because H naught of n is already finite in duration. So if I multiply an IR response with an FIR in the time domain, I'm only as long as H naught of n. So that was good insight. Really good insight. I hadn't thought about that approach. Because what is this? This is really an LTI system with a pole on the unit circle. Two poles, one at pi over 2 and one at minus pi over 2. And it's a two-sided impulse response. Bibo unstable. So this is lab 2. Cosine generation. And so if you look at the three coefficient case, my averaging filter is 1, 1, 1. This filter, the signal is 1, 0, minus 1. So the product just becomes 1, 0, minus 1. Again, we have odd symmetry in the impulse response about the midpoint, and we have generalized linear phase. Really, really tough problem. Really tough problem. Any questions on? For regrades, talk to me, after lecture. But any questions on this one? We really do use this in practice. This is a very well used technique. So to build a spectrum analyzer out of this, all I need is to do an absolute value here out of every output. I just put an absolute value or absolute value squared. I now have computation of power in each band. I have a spectrum analyzer, uniformly spaced. And again, any low-pass filter will do as the prototype filter. And implementation is also not so bad. Right, these are all FIR filters. Okay. Now, as the number of channels grows too high, then the FIR filters become long, but you can do 512 channels here. And we can do 512 tap FIR filters, no problem. All right, now problem 4 homework set. I'm going to let you kind of work through this. Since it's potpourri in a lot of its opinion, you just have to fully justify your answers. I got all kinds of answers that I gave full credit or 2/3 credit to. Even if you argued probably the opposite of what we do in practice, if you argued it well, you got it. Right? So this is, make your case and justify it fully. So potpourri. So first question up. Assume the use of an A to D converter at the front end of a signal processing system. What are the design trade-offs in a signal processing system when increasing the sampling rate beyond twice the maximum frequency of interest? So there are two impacts here. Signal quality is a trade-off between signal quality and implementation complexity. So who wants to argue what happens to signal quality? You can argue this all kinds of ways. Go ahead.
Well, I said it's spread out the replicas and basebands filter better.
Right. So it helps you if you want to reconstruct from samples later. Right, it helps you do that more easily, right? Which is true. What else? What about the immediate impact on signal quality right off the A to D converter output? What happens when you oversample? Go ahead.
Well, if there's noise, then there's a higher chance of sampling noise, but you use a filter to remove the noise.
That's right. So more noise is getting through, right? Because you're at a higher sampling rate.
Wasn't the noise getting through anyway, but it's aliasing.
Right, exactly. So the noise is already getting through, it's just aliasing it in your band of interest. Now at least you've got a big chunk of that noise in a band outside of your band of interest, your frequency range of interest. That's actually a good thing because now I can filter that out. That's actually turns out to be a good thing. Now, what about aliasing in general when I increase the sampling rate?
You don't have as much. So you're going to have aliasing no matter what.
Always have aliasing, but if we oversample,
You'll have less.
I have less aliasing. So I have less aliasing anyway, and I have a better handle on at least some part of that noise up to half the sampling. Between the maximum frequency I care about and half the sampling rate, I now have a better handle on what to do with that noise. We're going to use oversampling like crazy coming up. Love oversampling. The sampling theorem is an excellent place to start, but we don't stop there. It just tells us that the sampling rate has to be more than twice the maximum frequency that we care about. Doesn't tell us that, right? What did you do in homework 0 and 1 when you're plotting signals and finding spectrum? Oversampled like crazy. Like how much?
I actually might do like
1,000 to 1. Why not? You know, it's in MATLAB. You know, the bandwidth was low. And why not 1,000 to 1? And in practice, we do 1,000 to 1 in data converters, which we'll talk about in lecture 10. 512 to 1, 256 to 1 for audio converter. It's coming up. So oversampling is a good thing. Well, for signal quality. But what happens in implementation complexity?
You need your processor to be fast enough to sample at that
Right.
rate.
So if I sample it 10, so if I sample it 10 times faster, I got to have a processor that can handle 10 times as many samples per second. So a lot of you said more samples, but you didn't tell me more samples per second is the key. So you got some credit for that. But what else happens in implementation complexity? Some of you did it. Some of you pointed it out very well. What happens to filter orders when you oversample?
Like they have you mean like filters have greater chance of being unstable? When you get higher orders, that would change.
Yeah, exactly. So you could argue it either way. So if I increase the sampling rate, the FIR filter order is going to go up because my transition band gets smaller. Right. The key. Not a problem. So if I were to tell you a passband frequency, let's say it's 2 pi, f pass over fs, and this is pass, and this is 2 pi f stop over fs. And here's FFS, maximum frequency, which is pi. So if I increase FS, this transition band gets smaller. I need a higher order filter to go from passband. So here's my passband. And several of you correctly, we pointed this out. All right, so there's my my low pass filter should fit in here somehow in terms of magnitude response. But again, if I increase the sampling rate, this distance gets smaller, harder filter. And then for an IR filter, it means I have a increased chance of fiber instability when I implement. Yeah, it's a problem. So there's going to be a trade-off, right? In theory, we love 1,000x oversampling, 1,000 times oversampling. But that means I have to process 1,000 times more samples per second. And my filter orders go crazy. And possibly drives my IR filters unstable.
Why does your filter order go crazy?
Well, you need to be able to transition from pass band to stop band. And the filter order is inversely proportional to this distance. I mentioned this in passing in class. So you didn't have to have that answer here to get full credit, but if you had the answer, it was good. So the filter order is proportional to this difference, this distance. And again, with increasing sampling rate, this distance is getting smaller, your order is getting higher. Now, if your filter order is increasing, now your buffer sizes also increase. So some people mentioned about buffer sizes increasing, but didn't tell me why. Normally they wouldn't increase. If the filter order is the same, then the buffer sizes aren't going to change. I still have to store the same number of current and previous input values and the same number of previous output values. Oh Lord. Quickly move on to part B. This is a real problem in designing systems, and someone had a very clever solution. I'm having trouble implementing this in fixed point. So what was the answer? What are you doing in lab?
Floating point.
Just floating point. Who cares about a DC offset? That shows up in your exponent. It doesn't affect your mantis and floating point. So one or two students just said, "Oh, we'll just use floating point." Sure, you're right. I mean, I hadn't thought about that answer, but yeah, why not? All right, if you're stuck with fixed point, I was thinking outside the box. You got full credit. Okay, so how would you suggest remove the so notch filter? So someone put down a filter and put us like a smiley face, which was the right answer. Anyway, notch filter at DC will do it. So a demodulation puts a lot of put a lot of values at DC. Last one is audio. I took a lot of answers on this audio question. I just wanted you to think through it. So the question was design a subwoofer, and who defended FIR? Go ahead.
Well, I have a question.
Yeah.
When you say DC offset, you mean values?
Yeah, it means that what happens is you get a signal that, let's say, has two components, plus some large constant. And this large constant can come from demodulation. Remember, for demodulation, I modulate, which gives me frequencies at 2F0 and DC. So there are a lot of things that I do in communication systems where I get a bunch of DC energy. And for fixed point, this kills you, because in fixed point, if you only represent numbers from, say, minus 16 to 15, and your DC offset is like 10, you've just killed a lot of your dynamic range. So we really want to get rid of this, as subtract off at least the mean value is one way to do it. Notch filter is another. Audio took a lot of answers, but I wanted phase in there somehow. Either way is fine, but some phase. All right, thank you so much.
But it makes sense.